Yeah, welcome to my talk. This is joint work with Stephanie and Robbert. He's here, but I can't see him. So this talk is about message passing. Usually in languages like Go or Rust, you have a channel type. In Rust, this is split into receiver and sender. And on those channels, you can send messages of a fixed type. But session types are a little bit more advanced. They are more flexible. So the type of the message that you send at a particular moment can depend on the state of the protocol. And that state can change as you send more messages or receive messages. And this is handled by linear types. So let's look at a simple form of session types, binary session types. Here we have a channel variable C, which has this session type. And the bank says that we receive that message. So first we receive a natural number, and then the type of C will change. And after that, you are supposed to receive a Boolean and then send a natural. So in binary session types, these come in pairs. And of course, the other side of the channel has a dual type in which all the sends and receives are interchanged. So we have seen now send and receive and end, but usually session types also have a form of choice, where one party decides it sends a Boolean or a bit saying, I want to go to the left side of the protocol or to the right side, and then the other party has to deal with that choice. We usually also have recursion, so we can make infinite protocols. And the type of message that we send are just the values in your language. But an interesting point of binary session types is that channels are also ordinary types, so you can also send them as messages over other channels. On the other hand, we have multi-party session types in which there are not two participants, but more than two. And in that case, we annotate these types with indices, indicating with whom we are communicating. So for example, in channel C0, that is communicating with participant 1. It's first sending a natural number, and then it's receiving a natural number from participant 2. And there is then some kind of rule about when these things are consistent with each other. And that's not just that the send and receive match, but also that they are done in such an order that there is no deadlock. So a lot of research has been done about session types, but I here want to focus on two families of languages, the GV family on the one hand, and the multi-party session types family. So the main difference is that GV has binary session types and the multi-party languages have multi-party session types. And then you may think that one is more general than the other, but that's not really the case. So in GV, you get deadlock freedom, which is the main property that session type people are interested in, by this duality and linear typing. And then the configuration of processes looks like a tree. And this tree shape is why you get deadlock freedom. So here, each vertex is a process, and a line indicates a communication channel. On the other hand, with multi-party languages, you have a fully interconnected topology, but then the deadlock freedom has to be ensured by this global consistency check. And this means that in the GV family of languages, you can have dynamic spawning, and in the multi-party languages, you usually have one static session, at least if you want to stay in the deadlock-free fragment. In the GV family of languages, you also have these channels as first-class values, whereas in the multi-party languages, you usually do not. And in GV, you have, it's all embedded in a functional language, whereas the multi-party languages are usually some kind of pi calculus. So here we want to, in this work, we want to combine the two to get all the strengths of the left, but also the more expressive session types of the right. And we call that combination MPGV. So what does that look like at runtime? How are the processes connected? Well, you still have a tree, but now in the tree are these small sessions with multiple participants. And inside each such session, the deadlock freedom is guaranteed by a global, but now local within that session check. And globally, over the whole system, the deadlock freedom is still ensured by the tree structure. So the main contributions here is the design of this language. So a language in which you are in a lambda calculus with multi-party message passing channels where they can be dynamically spawned, and they are first-class values. So we also have recursive types and choice and some other features. And using this, we can see that in our language, we really generalize the old GV. But actually, to do that, we have to add one additional construct, which also turns out to be useful for modular programming. So the key property here that all session type people are interested in is that by type checking, you guarantee deadlock freedom. And this, of course, deadlock can occur here because when you receive a message, you have to wait till the other side actually sends a message. So that creates a danger for deadlock. But here it's the case that if a program type checks, then that can't happen. And the method here of this is all mechanized in Coq. So let's look at what the main constructs are. So here we have a fork, and this is an NRE fork. So this is inspired by the multicode of Marco Carbone. And what this fork does, it combines channel creation with thread spawning, and this is essential for keeping this invariant that the configuration looks globally somewhat like a tree. So to this fork, we pass some number of closures, and into these closures, a channel will be passed. And the fork also returns a channel. So what we require here is that this factor of session types of each channel, that they are consistent in this multi-party way. And each child thread has to return unit in the end. And this is then the linear unit, which guarantees that this child thread actually consumed its session type fully. So here you see a picture of what that does to the configuration at runtime. So on the left, you see this red dot. This process is trying to spawn some children, and then it just grows an additional session. But the invariant that the configuration looks like that is then preserved. Here are simplified types of send and receive. So in the real system, you can have this NOE choice, so they are a little bit more complicated, but here we do without choice. So what send has as input is a channel, on which we are now allowed to receive, and it also a message that we are going to send, and then it returns the continuation channel with the new type after the send has been performed. And receive is the other way around. This returns the message that was sent. And if you're allowed to send channels as messages, that also has an effect on the shape of the configuration. So here we see that two processes are trying to communicate, and the process is going to send its connection to the other session, and that changes the shape a bit. In general, this can be a little bit more complicated because the messages here can also be pairs of channels or lists of channels, so then the transformation is a bit more complicated. Another thing is that in the real system, we have an asynchronous semantics. So that means that there is also some kind of intermediate state. So the pictures are not exactly like this, but if you want to see the details of that, you have to look at the paper. So close is the last operation. This is very simple. You can only do it if your session has ended. And what that does, it just throws away all the connections a process has to that session. And you see that this tree can get disconnected. This is not a problem for deadlocks. But on the other hand, you also see that this invariant is still preserved. So we wanted to show that this language is really more powerful than GV, and you may think that's already the case, because if you want a binary session, you just make one with 2 participants. But that doesn't quite work, because in this multi-party type system, the types have these indices indicating with whom we are communicating. And so if you just naively translate a GV program to this language, you may end up in cases where these indices don't match. So for that, we just introduced this redirect operation, which redirects messages from one destination to another, which then allows us to change this in the types. And this also turns out to be important for modular programming. And then in this translation from GV to MPGV, we need to insert this in particular places. So you may not know this, but the session type literature, and in particular the multi-party session type literature, has some problems. So here is a quote from David Castro-Perez from paper in PLDI 21. So I think they were the first to mechanize anything about multi-party session types. So they say, unfortunately, the more complicated the behavior is, the more error-prone the theory becomes. The literature reveals broken proofs of subject reduction for several MPST systems, and a flaw in the decidability of subtyping for asynchronous MPST, all of which are caused by an incorrect understanding of the asynchronous behavior of types. So that's why we also mechanized everything in Cork. So the language definition is about 500 lines. The proofs are about 10,000 lines. And this works with a small step asynchronous semantics with threads and buffers. So the simple theorem is safety. This says that threads don't get stuck except on a receive. Then deadlock freedom says that globally, even the receives don't get stuck on each other. And we have leak freedom, which says that messages don't get left behind. Another problem, which does actually occur in practice, is that you may not always mechanize the theorem that you think you're mechanizing. So how can you now ensure that this actually happened, that you did actually mechanize something non-trivial? So our deadlock freedom theorem is rather complex, so it's about 5 lines of code. And the statement relies on some auxiliary definitions, which are about 100 lines of code. So how do we know that this theorem actually says something non-trivial? So we think that you should always prove an easy to understand corollary, which it would be impossible to, which you know for sure is saying something non-trivial, but which a reviewer can immediately recognize as, if you prove this, then you have really proved something. So in our case, we proved global progress, which says if you start with a well-typed program, and that program steps to some configuration, then either the configuration is empty or it can step again. So this is not a very powerful theorem because, for example, if you have any thread that's just in a loop, then this theorem holds, but it would be almost impossible to prove this theorem by accident. So this theorem can be stated in one line and requires no auxiliary definitions. So this is just as a sanity check on the deadlock freedom statement. And yeah, I think this is very important. So what's in the paper? So we have the full language definition and semantics. So we have an asynchronous semantics, we have choice, we have recursive types, recursive session types, which can also be mutually recursive. We have linear types and unrestricted types, which you can freely copy and discard. We have multi-party consistency and global types, if you know what that is. So we have a description of the deadlock freedom proof in pictures, but also in formal detail. So in Cork we use separation logic for this. We have an encoding of GV in MPGV using this redirect. And all of this has been mechanized in Cork. So that's my talk. Thank you for listening.